The scientific revolution, as it has come to be known, took place in Europe in the 17th and 18th centuries. During this time, humanity made unprecedented advances in engineering, science, and technology, and essentially laid the foundations for modern science. The impacts of this era can still be felt all around the world today. One of the major mathematical developments which underpinned these unprecedented advances in so many scientific fields was the discovery of calculus. Calculus is the mathematical study of change, in a similar way to geometry being the study of shapes. It was developed in the 18th century by Isaac Newton and Gottfried Leibniz, and it's no coincidence that so many advances in so many fields followed their discovery of calculus. Calculus has so many applications that it would take us hours just to name them. Even in your everyday life, calculus is used to make calculations and predictions. It can be used to calculate the volume of an oddly shaped container. It's used to design your car and its safety features. And even your Xbox couldn't function without calculus. It's also used in labs all over the world every day to calculate things like tension, arc length, rates of growth and decay, and the list goes on and on. In our presentation today, we're going to focus on one specific application of calculus, tangent lines. We're going to explain how to find a tangent line and its slope, and show you how they are used in your everyday lives.
Firstly, we're going to explain the fundamental principle of calculus, the derivative. Calculus is based on finding limits of infinitesimally small intervals. What does that really mean? Let's look at an example from S.L. Sallis and Einar Hiller's Calculus, 1 and Several Variables, Part 1, 3rd edition. Plants grow at a constant rate. We can measure this by looking at the growth of a plant over several weeks and comparing the data. But what if we wanted to measure the growth over a matter of seconds? We can calculate this by finding the gradient of a single point on the curve in accordance with the definition of a derivative, which is f a plus h minus f of a divided by h. We are now better able to find the growth rate at a single point. This means that we are able to calculate the growth of a plant at smaller and smaller intervals until we reach our desired time frame. This concept can be applied to other mathematical functions, such as curves. A simpler way of finding the slope of a curve at a single point is by finding the equation of the tangent line.
Imagine for a moment that you're riding a roller coaster at an amusement park. Your heart starts racing as you reach the big dip right before you fall downwards. The ride gets steeper and steeper until you reach the bottom. But what if you wanted to calculate the steepness of the roller coaster at a single point? That's where calculus comes in. Differential calculus deals with the rate of change of functions through the use of derivatives and differentials. Now, let's place the same curve on a Cartesian plane and label the x and y axes. Draw a line that touches the curve at one point without cutting across it. This is called the tangent line. By finding the equation of the tangent line, we are able to derive the steepness of the roller coaster at a single point. The equation of the tangent line can be found by following 4 simple steps: finding the derivative of the curve, plugging in the x value of the given curve to get the slope, finding the y value of the point with the original equation, and lastly, plug the known values into the point-slope equation. Now, this is the kind of example of something you might find in an exam. A good first step is to write out the equation itself and the associated point, also to point out which one is the x and y value for later reference. So let's do that now. Alright, now that we've done that, let's go ahead to our first step, which is to find the derivative. Now I found the derivative by using the sum and difference rule as well as the power rule. So on to the next step. So the next step is to substitute x into the derivative to find the slope of the curve. So let's do that now. Now, if you were to solve this, you would get a slope of 5. So let's write that out. Now that we've done that, the next step is to find the value of y. But the great thing of this example is that actually in the point, we've been given both a determined x and y value. So as we can see here, the y value is 3. So you can actually miss this step in this case. Okay, the final step is to substitute the known values into the point-slope equation. So the point-slope equation is y minus y1 equals m times x minus x1. Now you would substitute the known factors such as the x value, y value, and the slope into this. So let's do that now. Now what we should do is we should expand this equation. Now if you were to solve this out, the equation that you would get for the tangent line is the following. Y equals 5x minus 2. And there you have it, your equation of the tangent line. So here is another example of something you might find in a quiz or an exam. Now, as I said in the last example, a good thing to do is to write down the function itself. And the associated point. Now the first step, as we remember from the last example, was to find the derivative, so let's do that now. Now I found this by using the quotient rule as well as the sum and difference rule. Now, the next step is to substitute x into the derivative in order to find the slope. Now, as you see here, the x value is 2, so let's put that in. Which equals minus 1. Therefore, the slope equals minus 1. Okay, and we do know our y value in this example, so we can skip that step. Finally, we're going to substitute this into the point-slope equation. And if you expand this out, the equation that you get is going to be y equals minus x. And this is the equation of the tangent line.
Now you have seen how finding the tangent line can be useful in the simple scenario with the slide. How might you see it in a scientific environment, say when you're at university? A good example to look at is population growth. So imagine you're doing research on the population of a town in a third world country. The mayor is thinking about building a new school and wants to know how many children are likely to attend. You have already graphed the population change over the last 10 years, and you want to know how fast the population was changing at a given point on the curve. Let's imagine for simplicity's sake that the population change is given by the function 2 to the power of x, a simple exponential function, meaning we raise 2 to the power of the amount of years since the starting point to find the population in a given year. Firstly, we find the derivative of the function as we did in our first example. We then plug our x value into the derivative to give us the gradient of the tangent, and there you go. High gradients mean that the population is changing very quickly, and low gradients mean it's changing more slowly. This is useful information when looking at population growth, as well as nuclear decay, bacterial growth, and many more things you may encounter at uni.